Okay, so the last video picked up on this example here. I was having some audio issues, and hopefully from it pretty soon it'll get worked out. This particular mic that I have now is not the best, but it'll get us by for now. Here we're doing a confidence interval on this population mean mu, the average age of all people in the civilian labor force. And that's our mu is our parameter of interest, and it's unknown. And so what we're going to do here is we're going to use this formula here. And it's the only confidence interval formula we have so far. X bar plus or minus z sub alpha over 2 times sigma over root n. We're going to use that. We're going to use that because we can use that formula for three reasons. We have a random sample. Two, we have a large sample. For us, large was more than 30. And here we have a sample size of 50 people. And 3, sigma equals 12.1. That's known. Okay. So what we have is this formula. We want to use that. Well, from our sample, so what I've done, let me back up. What I've done with this formula, I've said, okay, we're going to use this formula to estimate mu with an interval, and I've justified it by these those three points there. In order to use this formula and it be valid, you have to the appropriate conditions have to be satisfied, right? So here there were these 3 assumptions that we looked at up here, and they need to be satisfied in order to use this formula there. Okay, so going back here, so what do we know about from our sample? From our sample, we have the following, that X bar is 36.4, N is 50, sigma is 12.1, z sub alpha over 2. This is a percentile from the standard normal distribution. Here alpha is 0.05 because I have a 95% confidence interval. So I'm looking at z sub 0.05 over 2, which is z with the subscript of 0.025. Okay, and you recall what that is. I'm going to come up here and draw the table, or draw a picture. For the standard normal distribution, that is the z value, such that the area under the curve to the right of that value is 0.025. And when you use your table from the front of the book, your normal distribution table, you'll see that this value is 1.96. Now remember, when you're using your table, it gives us areas to the left of a z-score. So the area to the left of this z-score is 0.975, and so you look for a z-score that corresponds to a left area of 0.975, and you should get 1.96. So what we have from our sample and from our confidence level is those 4 pieces. So now the interval, the computation is fairly straightforward. Alright, so if I'm going to use this formula here, X bar plus or minus z times sigma over root n, just going to plug in 36.4 plus or minus 1.96 times 12.1 divided by the square root of 50. Okay, so just plugging in those values, and I'm going to simplify first this ratio. So that simplifies to, if you punch it in your calculator, you'll get 1.71. This is actually the standard error of x bar. Okay, or really an estimate of the standard error of x bar. We had talked about that earlier in this class. Multiplying 1.96 and 1.71, we get 3.35. This is what's called the margin of error. Okay, the margin of error. And I'll talk at length about the margin of error in a little bit. And so what I'm going to do here is I add and subtract 3.35, and if you take, so the lower bound is 36.4 minus 3.35, comma, the upper bound is 36.4 plus 3.35. That's giving me a lower and an upper limit for this interval, and that lower limit turns out to be 33.05, and the upper limit is 39.75. Okay, so make sure you can verify all that arithmetic there. I may have gone through it quicker than you can punch in your calculator and follow the lecture, but make sure you verify all of that arithmetic. So this is our interval. Now, we think that mu is in this interval, 33.05 to 39.75. Now, are we certain that it's in there? No, we're not certain. We're 95% confident. Okay, so we have the computation of the interval. I also want us to look at the interpretation of the interval. It would look something like this. We are 95% confident that the civilian workforce, or that the mean age of the civilian workforce is between 33.05 years and 39.75 years. Okay. So what does that say? We're pretty sure. I mean, there's a 5% chance that our method yielded an interval that's not correct, but 95% of the intervals that would be yielded by this method using this formula here would be correct. Okay, so is this particular one, 33.05 to 39.75, correct? We don't know. We would just say we're 95% confident. All right, so a takeaway for this interval might be, if somebody comes along and says, well, I think the average age for the civilian workforce is actually 44. Well, this interval would suggest that that's very unlikely. Okay, and we can use the interval in that sort of way to kind of test somebody's statement about a parameter. And we'll actually look at that later on in a formal way called hypothesis testing. All right, so that's the confidence interval. That's the 95% confidence interval. If you wanted a 90% confidence interval, you could do the same sort of computation. Everything would be the same, except this would change right here. The z value would change. It would be z, that would change. It would be z sub 0.10 divided by 2. So you would ultimately be looking for z with a subscript of 0.05. That z-score is 1.645. And with that z-score, you would actually get this interval here. I'm not going to work through it. I'm going to let you work through it. You can check to see that you get 33.59 and 39.21. Okay. Notice, I want you to notice that this interval is a little bit tighter than the 95% interval. The width is a little bit shorter there. Okay. And the reason that's the case is for us to be less confident. In other words, our confidence level went from 95% to 90%. For us to be less confident, we had a trade-off, actually a gain in the interval becoming more narrow. That's actually a good thing, the interval to be more narrow. Okay. All right, so continuing on here. Big question. You may want to hit the pause button here. But anyway, this is the question that we need to take a look at, given this is a graduate course. Here's a formula. Where does this formula come from? All right. How does someone come up with these endpoints? That confidence interval for the population mean. Where does that come from? Well, it turns out it's a result of the sampling distribution. And I want you to recall from previous lessons that X bar, or really in particular, X bar standardized, which we would write this way, X bar minus mu over sigma over root n, is distributed standard normal, that is normal 0, 1. If our population is normal, so if the population we're sampling from is normal, or we could also look at that same ratio, X bar minus mu over sigma over root n. That is approximately standard normal if our sample size is large. Okay, so why did I make a big deal about that? Those two conditions or assumptions, the population is normal or the sample size is large. You go back to our interval formula here, notice that is assumption 2, normal population or large sample. Okay, so with that in mind, we have that these ratios follow a normal or a standard normal distribution. And so I'm going to say, let's consider the following picture. Okay, so here I've got the standard normal curve, and I'm going to pick off an upper value z sub alpha over 2 and a lower value negative z sub alpha over 2. Those are going to be equidistant from 0 because the distribution is symmetric about 0. Okay, so when I think about these values, that right tail area is alpha over 2, the left tail area is alpha over 2, and the area in the middle, okay, what's that? Well, recall the total area under the curve is 1, so this area in the middle here is going to be 1 minus, what do I have? I have alpha over 2 plus alpha over 2. That's what's left over in the tails, and that would be 1 minus alpha. So the area under the curve between these two z values is 1 minus alpha. So I'm going to think of this mathematically as, well, the probability that any z random variable that would fall between negative z sub alpha over 2 and positive z sub alpha over 2, that probability is 1 minus alpha. Okay? Well, that's just a normal distribution idea. I can replace this z value here with anything that follows a standard normal distribution? Well, what follows a standard normal distribution? This ratio is the same thing, but that ratio follows a standard normal distribution, so I'm going to replace that z value there. Let's see here. So putting in here, we got x bar minus mu over sigma over root n less than z sub alpha over 2 equals 1 minus alpha. Alright, so what would you do to get a confidence interval formula? Basically, we're trying to get a lower bound and upper bound, and the lower bound is within this formula here, x bar minus z times sigma over root n, and the upper bound is x bar plus z times sigma over root n. So what you would do is, at this point, the goal is to get mu in the middle. Okay. That's the goal. So algebraically, what I would do here, so this may be in this course the most mathematics that we would have to do, maybe the most difficult mathematics. We want to get mu by itself. Alright, so to get mu by itself, I'm going to multiply everything under the probability statement by sigma over root n. Okay? So if I do that, then what I have left over in the middle is just x bar minus mu, and what I have, say, on the right hand side is going to be z sub alpha over 2 times sigma over root n, and then on the left hand side I'm going to have a similar quantity, but negative z sub alpha over 2 times sigma over root n. Okay, and again, the probability of that happening is 1 minus alpha. And all I've done is do a little algebra within that probability statement. The next thing we would do is, we want to get mu by itself, so I'm going to subtract x bar from everything in this inequality here. So if I subtract off mu, or x bar, I'm going to have minus x bar there. And in the middle here now, I'm just going to have minus mu. And on the the upper part, I'm going to have negative x bar plus z sub alpha times sigma over root n. And that entire probability is 1 minus alpha. Okay, well, so what I actually have here is a confidence interval for negative mu, because I have negative mu in the middle. Well, I want positive mu in the middle. So what can I do? Well, I can multiply everything under the probability statement by negative 1. And if I do that, you have to recall an algebra rule that says if you do that sort of thing, you need to switch the sign. Okay, so I can multiply this by negative 1, and I would have x bar plus z alpha over 2 times sigma over root n. But this would be switched to greater than. That's a positive mu. This is greater than. And this would become x bar minus z sub alpha times sigma over root n. And that would equal 1 minus alpha. Okay. What I'm going to do next is just rewrite, in terms of reading this inequality from left to right. We typically think of things as the smallest quantity being on the left side and the largest quantity being on the right side. But mathematically, the way this reads is that this x bar plus z times sigma over root n is bigger than mu, which is bigger than this quantity here. And so what I'm going to do is I'm going to flip everything. So I'm going to still have mu in the middle, but the smallest quantity is going to be x bar minus z times sigma over root n, and then the larger quantity is x bar plus z times sigma over root n. Okay? So we've got mu in the middle. All right, good. This right here is the lower bound for my formula. And this right here is the upper bound for my formula. Okay? So this formula, here we've done what's called the derivation of this confidence interval for mu. That's kind of, some fairly sophisticated mathematics, and we have derived the formula, and it's all based on the sampling distribution of x bar minus mu over sigma over root n. Okay, and so anyway, that is the derivation of this interval formula, and we will stop this part of the video here. We're going to look more at confidence intervals in the next video.